IK Pegasi system sits 200 light-years away, silently waiting. According to NASA's latest data, the white dwarf star has increased its matter transfer rate from its companion star. This means only one thing: a kilonova explosion is approaching, and we cannot stop it. The question is, are 200 years enough for humanity to move to another planet? IK Pegasi appears as an innocent dot in our night sky, visible to the naked eye in the Pegasus constellation. But this binary system harbors one of the universe's most terrifying weapons. The white dwarf component, designated IK Pegasi b, is steadily accreting matter from its larger companion star, IK Pegasi a, at an accelerating rate. NASA's Chandra X-ray Observatory detected increased X-ray emissions from the system in 2023, indicating the white dwarf has entered its final feeding phase. The star has already consumed 1.2 solar masses of material and is rapidly approaching the critical Chandrasekhar limit of 1.4 solar masses that will trigger catastrophic collapse. The Chandrasekhar limit represents the maximum mass a white dwarf can support before gravity overwhelms electron degeneracy pressure. When IK Pegasi b crosses this threshold, approximately 50 octillion tons of matter will collapse in less than 2 seconds, creating temperatures exceeding 3 billion Kelvin and triggering explosive nuclear fusion. This collapse will release energy equivalent to 5 billion times our sun's total lifetime output, concentrated into a single devastating explosion. The resulting kilonova will outshine the entire Milky Way galaxy for weeks, becoming visible from Earth even during daylight hours as a brilliant new star. During the kilonova explosion, the white dwarf's core reaches nuclear densities, fusing silicon and nickel into iron peak elements, while simultaneously generating intense gamma-ray bursts. These gamma rays, moving at light speed, will arrive at Earth in exactly 200 years, carrying enough energy to strip away our protective ozone layer. The explosion will also synthesize rare heavy elements like gold, platinum, and uranium through rapid neutron capture processes. Ironically, this cosmic catastrophe that threatens Earth's existence will scatter the very elements that make technological civilization possible throughout the local galactic region. When the kilonova's gamma-ray burst reaches Earth, it will deposit approximately 100 kilojoules of energy per square meter of our planet's surface. This radiation will dissociate nitrogen and oxygen molecules in our stratosphere, creating nitrogen oxides that will rapidly destroy the ozone layer, protecting us from solar ultraviolet radiation. Within hours of the gamma-ray arrival, Earth's ozone protection will be reduced by 75%. The resulting UV bombardment will trigger mass extinctions in phytoplankton, collapsing marine food chains and eliminating the organisms responsible for producing 70% of our planet's oxygen supply. The UV radiation increase following ozone depletion will prove lethal to most surface life forms. DNA damage rates will increase by orders of magnitude, overwhelming cellular repair mechanisms. Plants will experience photosynthesis breakdown, while animals face skyrocketing cancer rates and immune system collapse from radiation exposure. Agricultural systems will fail within months as crops succumb to UV damage and soil microorganisms die off. The global food web will unravel from the bottom up, starting with photosynthetic organisms and cascading through all trophic levels, potentially causing a mass extinction rivaling the Permian-Triassic event. The kilonova's optical light will heat Earth's atmosphere temporarily, but the destruction of ozone and subsequent loss of photosynthetic organisms will trigger a global cooling event. Without plants absorbing CO2 and producing oxygen, atmospheric chemistry will shift dramatically, reducing the greenhouse effect. Global temperatures could drop by 1–2 degrees Celsius within a decade, initiating an ice age that could last thousands of years. Ocean currents will shift as thermal gradients change, further disrupting weather patterns and making large portions of Earth uninhabitable for complex life forms. Astronomers monitor IK Pegasi through multiple wavelengths, tracking its accretion rate and mass transfer efficiency. Current models suggest the white dwarf gains approximately 10 circumflex 7 solar masses annually, putting it on track to reach the Chandrasekhar limit within 200 years, though this timeline could accelerate unexpectedly. Space-based telescopes continuously observe the system for signs of increased activity. X-ray brightening, spectral changes, or
99%.
orbital period
All
variations
parameters
that
nominal.
might indicate the final approach to criticality. Unfortunately, even with advanced warning, we cannot influence or prevent this cosmic event from occurring. Underground cities could protect small populations from initial gamma-ray bombardment and subsequent UV exposure. Nuclear submarines and deep mines might serve as temporary refuges, though long-term survival would require closed-loop life support systems capable of operating without surface resources. Space colonization represents our best long-term survival strategy. Mars, with its thin atmosphere and greater distance from the Kilonova, might experience less severe effects. Establishing self-sufficient colonies on Mars, the Moon, or space habitats could preserve human civilization beyond Earth's potential sterilization. Advanced geoengineering projects could potentially mitigate some Kilonova effects. Atmospheric processes might artificially maintain ozone levels, while orbital mirrors could regulate solar radiation reaching Earth's surface. However, these technologies remain decades away from development and would require unprecedented global cooperation. Genetic engineering could enhance human radiation resistance and UV tolerance, potentially allowing surface survival in the post-Kilonova environment. Enhanced DNA repair mechanisms, improved cellular defenses, and modified photosynthetic symbiosis might enable adapted humans to thrive in the transformed world. Generation ships or advanced propulsion systems could transport human populations to nearby star systems beyond the Kilonova's deadly influence. Proxima Centauri, Alpha Centauri, or Wolf 359 might serve as potential destinations, though journey times would span centuries even with advanced technology. Breakthrough Starshot and similar projects are developing technologies for interstellar travel, but scaling these systems for human transport presents enormous challenges. The 200-year timeline provides a narrow window to develop and deploy interstellar capabilities before the Kilonova renders Earth uninhabitable. The IK Pegasi Kilonova represents a natural phase in stellar evolution, part of the cosmic cycle that creates and distributes heavy elements throughout the galaxy. These explosions have shaped galactic chemistry for billions of years, enabling planet formation and life itself to emerge. While threatening to our specific civilization, kilonovas are essential cosmic events that seed space with the materials necessary for future generations of stars and planets. Our challenge is surviving this particular explosion while understanding our role in the vast interconnected web of cosmic evolution. The IK Pegasi Kilonova countdown has begun, marking humanity's transition from a single planet species to a cosmic civilization. We have 200 years to develop the technologies and wisdom needed to survive our first existential cosmic threat. The universe has issued its challenge. How we respond will determine whether human consciousness continues beyond Earth's boundaries.